Good morning. Thank you for joining us for the Introduction to Combustion webinar conducted by the Industrial Heating Equipment Association with presenter Michael Cochran from Bloom Engineering. I am Brian Kelly with IHEA member company Honeywell Thermal Solutions, and I am the chairman of the IHEA Education Committee as well as the Combustion Seminar, and I also serve on the IHEA Board of Directors. If you're not familiar with IHEA, it is a professional trade organization association representing the major segments of the industrial heat processing equipment industry. We'll be taking questions from anyone viewing the webinar today. You can ask those questions in the chat box, and Michael will address them during the seminar. There also will be a very brief survey at the conclusion of this webinar. We would appreciate your feedback, as that's invaluable for these types of activities that we present here as part of the IHEA organization. With that, I'd like to introduce our presenter for today's webinar, Michael Cochran. Michael earned his bachelor's and master's in mechanical engineering at Notre Dame. He's also worked at a furnace OEM before landing at Bloom Engineering in Pittsburgh. He's been with Bloom for 6 years and is currently the marketing engineer specialized in combustion systems. Also has served as an applications engineer and is interested in the thermal modeling of steel furnaces. With that, I will give it to Michael for this webinar.
Well, Brian, thank you so much. I am Michael of Bloom Engineering, and thank you to all of the attendees for your interest either in combustion, in IHEA, or in both, or just needing something to do to get you through to the weekend. We know that the title is Introduction to Combustion, but I think we should first figure out what is combustion. It is, as everyone knows, a rapid, high-temperature exothermic redox chemical reaction between an oxidant and a fuel, which is usually atmospheric oxygen, that produces oxidized, often gaseous products and generally releases energy in the form of heat, and there will be no quiz on that. In case you're having a little trouble remembering all of those words, or chemistry happened too long ago in high school, another way to think about it is fire. Why study combustion? Well, there are three main reasons that I like to study combustion. One, it is useful. Two, it requires caution when using. And perhaps most importantly, it is fun. There are many, many uses for combustion. The three I like to call it the three I's of combustion: increase temperature, incinerate, or illuminate. Throughout history, there have been countless processes that use combustion to do one or more of these three things: heat up, burn up, or light up. Many, some counts would say most processes in the industrially advanced world use combustion in some way or another. And in fact, combustion was one of the key elements that started the Industrial Revolution, when they figured out how to use the internal combustion engine. It does require caution. I'm sure that many of you have seen this photo or others like it. On May 3rd, 1937, a blimp called the Hindenburg left Frankfurt, Germany with 97 people aboard. 3 days later, after an uneventful trip across the Atlantic Ocean, they were docking near Lakehurst, New Jersey, and the details are a little sketchy, but the result is apparent. Right here, we have what we would consider uncontrolled combustion. 36 people died out of the 97 aboard. And what happened is they filled this blimp with hydrogen, which is lighter than air. And we'll see later why hydrogen would have been a bad choice for that. But we have uncontrolled combustion. Accidents can happen. We need to be careful. We need to respect combustion. We don't need to be scared of it, but we need to be respectful of it. And it is fun. I was a little boy once, and as most little boys, I liked to see fire. I thought it was cool, and I never thought that in my professional life I would be able to do combustion, and that's what has kept me interested for the last 10 years or so. Hopefully I can infect you a little bit with my enthusiasm and show you that combustion is fun. Before we get too much farther, I want to make sure that we have a common set of definitions so that we understand some of the terms that we're going to use. A British thermal unit, also known as a BTU, is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. The calorie is the amount of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius. So these are units of heat or energy that we will use. Particularly in this talk, I'll be using the British thermal unit, but you may run across the calorie or some other similar unit. The specific heat is the amount of heat required to raise a temperature of 1 pound of a substance 1 degree Fahrenheit, or 1 kilogram of a substance 1 degree Celsius. So what that means is this little chart shows you that different substances have require a different amount of heat to raise the temperature. Because we defined it in such a way, water, of course, will have a specific heat of 1 in either system. Steel and diamond, for example, for all of you who might have a big diamond out there you're wanting to heat up. If so, let me know. You and I could be good friends. I could show you how to heat it. You provide the diamond, I'll provide the heat. It sounds like a good arrangement to me. But anyway, the point here is that heat is an input that you use to increase the temperature of a substance, and each substance will have a unique specific heat. What is required for combustion? There are 3 things that conveniently form a triangle: fuel, oxygen, and some source of ignition. Get those together and you can have combustion. For fuels, most often we'll see those as a hydrocarbon, which is a substance that's made of hydrogen atoms and carbon atoms that join together into molecules that will combust later. Many times, and particularly in industrial applications, but also in residential applications, your furnace, which if the weather has been anything like it is in Pittsburgh where you live, you have been using your furnace quite a bit over the last few days. But the fuel there is often in a gaseous form, such as methane or propane, or there can be process gases such as coke oven gas or blast furnace gas. Many different forms of fuel. All of those that I've just mentioned have one thing in common: they're made of hydrogens and they're made of carbons mixed in various specific combinations. There are other forms, such as a liquid, say an oil or gasoline for your automobile, and solids such as wood or coal. The important thing is, though, that in order for these substances in either liquid or solid form, for them to combust, they actually have to become gaseous in some form. So when your coal is burning, what actually happens is, not to get into too many details, but there's actually the hydrocarbons form a small gas as they heat up, and then they combust. Oh, I meant to mention that just like with the Hindenburg we saw, that source of fuel is not technically a hydrocarbon. It was pure hydrogen. So not all fuels are hydrocarbons, but the vast majority of fuels used commercially or industrially are going to be a hydrocarbon. Oxygen, which is the second leg of the combustion triangle, that is available in atmospheric air. Look around you in your room there. Look around and look at the air. I'll give you a second to do that. If you had superpower vision, you would see that approximately 20% of that air is oxygen and about 79% is nitrogen. Atmospheric air is readily available. However, if you're going to use it to propel a combustion system, then you'll need a fan or a blower. There are some systems where you can use a pressure difference to drive that combustion, but generally it's going to be a fan, a blower, or something like that. It is also possible to use pure oxygen. The problem is that is not readily available. It has to be purified, separated out from the nitrogen, and that is a utility expense. That can be piped in or crated in or something like that, bottles of oxygen. It is more efficient, but it is also an ongoing expense, whereas air is readily available, and there is an expense associated with the fan or the blower, the electrical cost of that, but the air itself does not require any utility expense. It's also possible to do a hybrid system, which is going to be somewhere between atmospheric air and pure oxygen. So generally what happens is you have a stream of air, the 21% oxygen, 79% nitrogen, and you squeeze in or bleed in a little bit of oxygen so that you can bring that percentage up to, well, anything over 21. Generally 35, 40% is a common range that you might use for a hybrid or oxy-fuel system. Above that, you might as well just go to pure oxygen. I want to remind you that if there are any specific questions, don't hesitate to interrupt me. I always think it's better to address questions as they come up, rather than waiting till the very end to try to figure out what I said maybe half an hour or 40 minutes ago. The source of ignition, which is the third leg on the triangle, there are several different types. Say a direct spark ignition, such as your spark plugs in your automobile. You could have a small pilot, like I have on my water heater at home, or you could simply use the temperature in the chamber. If you have a process, say a reheat furnace or something like that, where the temperature might get very high, anything above 1400 or 1600, then often you can introduce if the temperature is that high, you can introduce the air and the gas into that chamber, and it'll be hot enough that it will ignite and combust on its own. There are subsets of these. For example, I was thinking about it when you watch the survival shows and you rub two sticks together. That is a very difficult way to do it, but what you're doing is you're raising the temperature of those two sticks. You're getting enough heat there that you can actually combust the materials. So that would be an example of a temperature ignition. And if you have flint and steel, that's obviously a direct spark ignition. One important key that I won't be able to emphasize enough is that you need these three elements in the proper proportion. So if, for example, on this sketch here, we have the oxygen leg has become very small. You're starved for oxygen. Your fan shut off or something like that. Suddenly you have an overabundance of fuel, and there's a little crosshatch across the flame, which means that you will not get combustion in that case. So we need to keep them in a certain range of fuel and oxygen amounts, and I will go at great length over the next few minutes to discuss what those ranges are and how we calculate what those proportions are. The proper proportion is known as the stoichiometric ratio, which means the proper amount of oxygen or air required to combust the fuel completely with no oxygen and no fuel remaining after the reaction. So at your next cocktail party, you can impress your friends and colleagues by knowing this $100 word here, stoichiometric ratio. Or maybe you need to go to different cocktail parties if this is the kind of topic that comes up. But in any case, what this means is that you have the right amount. It's like the middle school dance. You want to make sure that everyone is able to pair off and no one's lingering around the periphery, unable to enjoy, unable to take part. As an example, a common fuel is natural gas, and that is predominantly, it's almost entirely made out of methane, which is one carbon with 4 hydrogens, CH4. So in my example here, I have a molecule of methane, and I introduce it with 2 molecules of, in this case, pure oxygen, and we'll explore in a minute what happens in air. But when we have pure oxygen here, if you look, when those get together, you provide, of course, we should all realize that you need a source of ignition here, lightning bolt, a match, a spark, something like that. And out the other side, you will get 2 H2Os, hydrogens with oxygen, which is water vapor, and 1 CO2, carbon dioxide. If you look on the left side, but on the left side of that arrow, you can count 1, 2, 3, 4 hydrogens, and on the right side, 1, 2, 3, 4 hydrogens, and 1 carbon on each side, and then there are 1, 2, 3, 4, and 1, 2, 3, 4 oxygens. So what we have here is a stoichiometric equation. You have fuel and oxygen on the left side, and you have no fuel and no unpaired no molecular oxygen on the other side. Everything's burned up, nothing's left over. We have a perfect stoichiometric ratio. If you do that in air, now I am an engineer, so if you recall, I said earlier on that air was about 21% oxygen and 79% nitrogen, but as an engineer, I work in approximations. I like nice round numbers. So I'm going to round 21% to 20 and 79 up to 80. So it's 8 parts of nitrogen and 2 parts of oxygen in 1 unit of air. So here we have, everything looks remarkably the same, except you have this 8 parts of nitrogen in a little cloud that goes through the process, and it doesn't do anything. It just appears on one side and appears on the other. But the key to realize here is, if you look down here, fuel, 1 part of fuel and 2 parts of oxygen, or 1 part of fuel, and here we have 10 parts of air. You still have the 2 parts of oxygen, but you have 8 nitrogens that are coming along just to come along for the ride. A brief interjection here with nomenclature and definitions. We commonly hear terms such as higher heating value or gross heat and lower heating value or net heat. And it's crucial to understand the difference here. In our reaction that we just saw, and in any combustion reaction that you can ever, in any combustion of hydrocarbons that you have, there will be water. You see that here, the H2O. Those are water molecules. So what happens is, water is a product of combustion, and in vapor form, it holds a lot of heat that is not available. If you think about boiling a kettle of water or a pot of water on your stove, it takes a long time for that pot to boil. More if you're watching, less if you're not watching. But that water vapor is carrying away a lot of heat. And when we have a combustion process, unless we're really tricky and really fancy, that heat is not anything that we'll be able to recover to use later in our process. It's just lost up the chimney. So the higher heating value is the amount of BTUs or calories for a an amount of fuel that you can get out of it. So if you burn it, you get an amount of fuel, or I'm sorry, excuse me, an amount of heat. Some of that heat, the heat content of the water vapor, goes up the chimney, and there's no way you can do anything with that. What's left is the lower heating value, or the net heat. And for most hydrocarbons, the lower heating value, as a rule of thumb, is about 90% of the higher heating value. That varies somewhat by a few percent depending on the specifics of the hydrocarbon. But generally it's about 90%, and that's lost into the water vapor. Now, as a trivia question here, for pure carbon, such as coal, the higher heating value equals the lower heating value for pure coal. And why is that? Let me give you a few seconds to ponder it. Let me go back here so that you can look at it for a second. Think about what's happening if you have pure carbon. So over here with the fuel, there are no hydrogens here. It's just pure carbon. And the details of how many oxygens are not relevant, but that means that what appears on this side? No hydrogens, so you can't have any water vapor on this side. So what that means is there's no water vapor. That means there's no heat content of water to pull off that extra energy. You're left with just pure carbon dioxide in your combustion. So because the heat content of water, as described here, is 0, then the higher heating value minus 0 is the lower heating value. So for the case of pure carbon, the higher heating value is equal to the lower heating value. And if you have any other fuels that are very deficient in hydrogen, then those numbers, the higher heating value and the lower heating value, will get closer and closer together. Again, for most hydrocarbons, the ratio ends up being about 90%. The proper proportion. So I had a picture a few slides back. Here I'm going to put numbers to it. So we have our CH4, which is our methane again. And this time we have 20% oxygen, 80% nitrogen, or 0.2 oxygen and 0.8 nitrogen. And if you recall, we need to get 2 molecules of oxygen to get stoichiometric combustion. So I multiply that 0.2 times 10. So 10 parts, and I get my carbon dioxide, my water, and my nitrogen. And of course, the point of the whole exercise, I get my BTUs. I get about 1,000 BTUs of heat energy. 10 parts of air to get this proper proportion. This number is dependent on the fuel. For methane, for natural gas, it's 10. For other fuels, that will be different, and it's specific to each fuel. And we report that as a ratio. So many parts of air for one part of fuel. Sometimes engineers get creative and come up with words like stoichiometric. Sometimes we are not creative and come up with terms like air to fuel ratio. So we call this the air to fuel ratio, and that again is dependent on the fuel. And the air ratio and the oxygen ratio are not equal. And let me repeat that. The air to fuel ratio and the oxygen to fuel ratio are not equal. That's because the air ratio has all of that nitrogen that comes along. And for pure oxygen, you don't have the nitrogen. So for methane, air to fuel ratio is about 10. Oxygen to fuel ratio is about 2. They will not be equal.
Michael, we did have a question come in, if you don't mind.
Oh, please.
All right. They are asking if the proportion would be cheaper introducing the nitrogen. Is that correct?
I'm sorry, if what would be?
The proportion would be cheaper introducing the nitrogen.
I'm sorry, if we could elaborate a little on the question.
Okay. So if we could have, I'm sure Jeff knows what he was asking. We could have him type a little more detail into the question box. That would be wonderful.
Yeah, thank you, Jeff. Let me come back here. This might be the cleanest place to talk about this, where we see the nitrogen right here, and we might be able to get a little clarity on the question here. And I appreciate the involvement, Jeff. I hope you don't feel put on the spot. You should win a little prize for having the first question here.
I don't see that there's anything else at the moment. Oh,
Okay.
here we go. Here we go.
Great.
Using nitrogen in a combustion furnace is cheaper to run using nitrogen instead of pure oxygen.
Well, yes, the point I was making earlier is that in many cases, because the nitrogen, it just comes along, it's mixed up with the oxygen in the air. So the air around you is readily available. No one charges us to use the air. So yes, there is no utility expense to using air, aside from whatever electricity you might need to use in the fan. With oxygen, in almost all cases, that's something that you would actually have to buy. It's a utility, such as your water or your fuel or electricity. There's a delivery charge. There would be a bill for oxygen. There are cases when it makes sense to use oxygen. There are cases when it makes sense to use air. And either of them will get you combustion, will get you heat, either the heat up, burn up, or light up that you might need. So the point I was making is that the nitrogen and oxygen that comes in air, you're not actually paying for it. Our government at this point has not found a way to charge us for breathing air. So we can use that freely as long as we have some way to deliver it to our combustion system. And I hope I was headed the right direction, Jeff. If you'd like a little more clarification, I'd be happy to provide that. Or anyone else out there?
Looks like that does it. Thank you,
Okay.
Michael.
Yes, and thank you. Please bring the questions along. That way I don't get sort of caught up in my own mind here. So the proper proportion, air to fuel ratio, 10 parts air to 1 part of fuel. Well, what do I really mean by that? In real life, it is very, very difficult to grab exactly one little molecule of oxygen and one little molecule of methane, make sure they get together and introduce a spark and make sure combustion happens. Molecules are so absolutely tiny that we can't see them, so we have to put a bunch of them together, one part. So what makes it even more difficult is that the density of gases, and remember both of these are gases, the fuel, methane, and the air, are both gases. So that means they change with temperature and with pressure. So what we have to do in order to get one common mass of oxygen or a mass of fuel, we have to define a pressure and a temperature. And the details are a little esoteric, and I would be happy to do this in the 201 level combustion course. But what it's important to remember is that the parts are based on a standard or normal condition, standard temperature and pressure. Some governing body out there has decided that at 60 degrees Fahrenheit and 14.696, not 14.697, psi, then that is the standard at which, when you have a gas and you have 1 volume of that, that's the standard. So we're talking about standard cubic feet. So we have a cubic foot, a 1 foot by 1 foot by 1 foot box at 60 degrees, 14.696 pounds of pressure. Whatever is in there, if that is air, then that's 1 standard cubic foot of air. And you need 10 of those to go with 1 standard cubic foot, 1 by 1 by 1 box of methane. And if you put those together, you can have stoichiometric or complete perfect combustion. Again, the details are a little bit advanced. The point is, there are standards by which you need to calculate the amount to get 1 part. And a brief note, standard conditions in the US, it's generally the standard conditions. Elsewhere, they call it normal conditions. I don't know if that means that the United States is not normal. I won't speculate on that. But anyway, there are different standards, and it's important to be aware of what standard you're using. So, proper proportion. 10-to-1 for natural gas, that's the natural gas or methane. That's the theoretical stoichiometric. And the typical stoichiometric, you'll recall, I hope, that long ago I mentioned that the percent of oxygen is actually 21% instead of 20, and I swept it under the rug and said, oh, we'll just use 20. But the actual stoichiometric is 9.55 to 1. And for calculations, we usually use 10 to 1. And for a normal operating ratio, we use 11 to 1. Everyone at this moment should have the following question. Why use a higher operating ratio? And just to point out, there are other fuels have their specific ratios. Propane is approximately, for our theoretical, is 25 to 1. The actual is 23.8 to 1, and so forth, butane. And these other fuels have a set air to fuel ratio. And I didn't put that in writing here, but this is the air to fuel ratio. The oxygen to fuel ratio would obviously be different. So why use this higher operating ratio? If we have a little bit of excess air, then what that does is it will ensure that there is no unburned fuel in the waste gas. No carbon monoxide, and you'll see in a few slides where carbon monoxide can come in. And that's an issue of safety. So as good as we combustion engineers might be, if we put exactly 9.55 parts of air in with 1 part of methane, there is a chance that they might not get mixed together quite right, and there'd be a little bit of fuel, a pocket of fuel over here somewhere that could pass through the chamber and enter the exhaust gas system. And I think that most of us would agree that having live fuel in your exhaust gas system is not something that we would all prefer to do. So what we do is we put in a little bit of excess air so that we make sure we get everything burned up and we don't have any unburned fuel go out our system. Here we have 10% excess air, and you can see this is not, let me repeat it, not a stoichiometric combustion reaction, because you have oxygen on the other side. You have a little bit of oxygen there. You have your carbon dioxide, your water, you have your nitrogen that came along for the ride, and here you have oxygen coming out the other side. Hey, Michael, you like excess air. Why stop at 10%? Is 20 better? Let's go to 30. Where does the madness end? Well, what happens here is that when you have excess air, remember that nitrogen goes along and does nothing except absorb heat. So you have to heat that up as well. Excess air gives you excess nitrogen, and that nitrogen absorbs heat, making less available for the process, and more nitrogen sucks up more heat. So if we look at combustion of a hydrocarbon here, and along the bottom axis here, along the x-axis, we see on the left is 0% excess air. So at, as we all should know by now, the term stoichiometric, perfect combustion, you release all of your heat. As you increase excess air, the slope or the trend goes downward. So when you get out to 80% excess air, then the nitrogen has sucked up so much of that heat that you can't use it, and it goes up the flue. So you're losing efficiency as you introduce more and more of this unburned, unburnable nitrogen into your process. 10% excess air is about right here. You'll see on the chart that that's still have 97%, so you're still in pretty decent shape. So you give up a little bit of efficiency, but you're staying safe. And that's the trade-off that we combustion engineers make, and I hope you can understand why we do it and agree that that's probably a pretty okay way to do it. What if we go the other way? Here's a rather extreme example. We see that we have the 10 parts of air, 8 nitrogens and 2 oxygens. And we have 2 parts, 2 standard cubic feet of methane. So we send it through our reaction, and out the other side pops 8 nitrogens. That shouldn't surprise you. 2 waters. But what are these odd things that we aren't used to seeing? 2 carbon monoxides and 2 hydrogen molecules. Those are actually molecules of unburned fuel. And one thing to note is that carbon monoxide is a deadly poison. Even in tiny, tiny amounts, it can cause headaches, dizziness, illness, and even brief exposure to high concentrations can have very bad long-term effects. So we want to avoid having carbon monoxide. It's not safe. But the reason this forms is we don't have enough oxygen molecules to pair up with the carbons to make carbon dioxide and to make water, H2O. There just aren't enough oxygens. So with a similar graph, again, you also lose efficiency. Here, it's not because you have all that nitrogen sucking up the heat. Here, it's because you simply didn't burn all the fuel. You turned it into a slightly different fuel. You got some of the energy out of it, but you're still left with unburned fuel, hydrogen and carbon monoxide in your waste gas, in your waste stream. That is unsafe. You're sending unsafe both to people who might be exposed to the carbon monoxide, but also to the waste gas system. If you think about it, you're sending waste gas up your chimney, or flue, waste gas stack, and eventually, when it gets to the outside world, it will come in contact with oxygen. If things are really off the rails, then what could happen is when you have the unburned fuel meet up with a source of oxygen, if it's hot enough or some other source of ignition exists, you could get combustion inside your waste gas system. Again, I don't think many people would like that. You're also paying for BTUs, energy that you don't use, that you're literally sending up the stack and heating the air above your plant. Your best practice, with a caveat to come in a minute, your best practice is always to maintain a slight amount of excess air. You want to avoid an air deficiency. You don't want to be fuel rich, that is. But remember that excess air leads to inefficiencies and can lead to process complications. If you're leaking too much air, you might actually overwhelm your waste gas system. You might overwhelm the stack. Now, the important caveat is that there are some processes that require something different than slight excess air, such as a galvanizing furnace. You will want to run a little bit air deficient. For a titanium forging furnace, you want to run with a lot of excess air, sometimes up to 30, 40 or more % excess air. Those are specific process requirements, and if you do not have those process requirements, if you're simply trying to get heat into a box, then the best practice is to have slight amounts of excess air and always to avoid the air deficiency or running fuel rich. Finally, on the right proportion question, there are certain limits before that combustion triangle falls apart. These are the lower and upper flammability limits, LFL and UFL, or also known as the explosive limits. These are particular to a fuel, often expressed as a % fuel by total volume. And the important thing to remember with these is that mixtures within these limits can combust. So if you have methane, any amount between 5% and 15%, combustion is possible. Now remember, there is only one point at which you have ideal stoichiometric combustion, but you can have some excess air, some excess fuel, and you will still combust. And these ranges are specific, as I said, to each fuel. All right. Since no one wants to ask questions, I will ask a question. How much air is required to combust 10 MMBTU, which is million BTU? All right. And is this a trick question? I didn't tell you what the fuel was. What if I'm talking about methane? What if I'm talking about butane? Methane, propane, butane are my three examples here. So the stoichiometric ratio is 10 to 1, 25 to 1, and 32 to 1. These have corresponding heating values. So for a flow for methane, it requires 10,000 standard cubic feet per hour. Propane is 4,000, butane is 3,077. The airflow, believe it or not, if you go back and do the math, is going to be 100,000 standard cubic feet per hour for each one of these, independent of the fuel. That's because the stoichiometric ratio and the heating value are such that you need the same amount of air to get a set amount of heat. 1 cubic foot of air, basically independent of the fuel, as long as you have a standard type of hydrocarbon, will be roughly 100 BTU of heat. Now this can change if you have some exotic mix, an off gas, blast furnace gas. This doesn't quite work out as well, but for a standard hydrocarbon, you're going to need approximately 1 cubic foot of air to get 100 BTU of heat. It's a neat little rule of thumb.
Michael, I do have another couple questions here that have come in.
Hey, go for it.
That's right. This one's a little lengthy, but I will let you know what they're asking. In my studies with several furnaces, I have noticed that using high reflective coating will allow close to stoichiometric combustion without CO. My conclusion is that reflected radiation increases the resistance time during which full combustion to CO2 is possible. What is your experience in using either high emissivity, high reflective coatings for enhancing combustion?
I always love when people start putting what they're hearing into their real life application. So I appreciate you thinking about this. So let me make sure that I understand the comment here. So what I think I'm hearing is that on a furnace with a high reflective coating, for example, on the refractory, that the operator is able to keep closer to a stoichiometric ratio without the danger of running into incomplete combustion.
It also goes on to say, during the same experiments, dropping 1.7 excess O2 to 0.7% improved specific energy efficiency by 7%. What are your experiences? How much does dropping O2 from 1.7% to 0.7% normally save energy?
Yes, what the comment there is, it's talking about oxygen in the waste gas stream. So 1.7% oxygen going down to 0.7% oxygen. What that means is he's running closer and closer to stoichiometric ratio, which, as we pointed out on this graph back here, if I can find, wrong direction. If we go back to this graph here, as you move closer and closer to stoichiometric, then you will have more and more of that heat available for your process. And when he was talking about the specific fuel number, that's how much fuel it takes to heat up a unit of whatever it is you're producing. So as you run closer to stoichiometric, then you will be able to have more heat available. So I absolutely would expect to see those kinds of numbers if you're making. I would expect to see those kinds of savings. That the 7% is maybe a little higher than I would have expected. If you're dropping from 1.7 down to 0.7, you must be doing a lot of things really, really right to get those kinds of numbers. But it's definitely not outside the realm of possibility, as you can attest. And what I can say is you must be doing some things right. You must have a good combustion system that you can run that close to stoichiometric without running into any issues with unburned fuel. So it sounds like you're doing a lot of things right. It sounds like your control system is in good shape, that everything's tuned up properly, and that number is believable. It's on the good end of believable. So I like the work that you're doing there.
Thank you, Michael. And just as a reminder, we can definitely get all of the information from these questions to Michael at the end of the webinar, and that way, if you have any more details you need to iron out, you can certainly do that directly with him. And then we also have another question after that last slide you had, Michael. It came through. Are these values equally applicable to forced draft and natural draft burners?
They absolutely are. So it doesn't really matter how the air gets to the process or to the burner. It still takes one standard cubic foot, and that is something I should have made absolutely clear on this slide, and I did not. One standard cubic foot of air, because remember, that is actually a mass. That is actually a number of oxygen molecules. So that needs to be one standard cubic foot of air gets 100 BTUs of heat. Now, on a forced, I think what might have caused this question is that on a forced draft type of system, you're actually physically squeezing the air because you have to push it through this fan and push it through the system. So you're squeezing it down. So a cubic foot of air has more oxygen in it than a standard cubic foot. And that sounds really confusing, and you need to sit there and think about it for a while. But the reason that question came up is that a cubic foot of air has different amounts of oxygen in it. You have to specify the standards. So this slide that's up on your screen right now should say 1 standard cubic foot of air will give you 100 BTU of heat. I thank you for pointing that out, and I will get that corrected before the next time we do this. So thank you. I will go ahead and move along to a summary. And again, thank you for the questions. I really appreciate this. In summary, combustion, uses of it. You can heat up, burn up, or light up. Many industrial applications, commercial applications, and even residential applications use combustion in some way. 3 things required: oxygen, fuel, and a source of ignition. And you've heard me say it, I don't know how many times, in the proper proportion. There's a distinction on higher heating and lower heating values, which is important and a little bit complicated, but it is important to make sure that when you're talking about heating values, you're using the right definition here. The stoichiometric ratio is fuel dependent, and because not many of us can run on a perfect stoichiometric ratio, it takes a darn good control system to do that. You often run with a little excess air, which is safer. You lose a little bit of efficiency because the extra waste gas, is particularly the nitrogen, carries off heat, and you lose some efficiency there. If you run excess fuel, that is unsafe. You're sending unburned fuel into the waste gas system. Carbon monoxide is always a potential danger, and it is always very, very bad for anyone who comes in contact with it. There are inefficiencies related to that as well, and that's because you're not actually burning all the fuel. Again, let me make it clear, there are some processes that require non-stoichiometric combustion, and if your process requires that, then I'll let you do it. But otherwise, I want you to run with a tiny bit of excess air. There are combustion limits. Remember that stoichiometric is 1 point, but you can have a combustible mix if you move to either side of that, and that can be a safety concern if you have some mix that is inside this sometimes slightly rather broad range. You could combust. And finally, the air requirement is independent of the fuel. I appreciate you guys romping through the world of combustion with me for about an hour here. I thank you, Kelly and Brian, for all the work you put into helping get this together. As Kelly said, if you have questions, she will be able to send them to me. I am happy to get back to you and expand on any of these topics. Early on in the talk, I said that it was fun, and I don't know how weird that makes me, but I think it is. So I enjoy exploring some of these questions and topics. So please be in touch.
All right. I guess I'm probably weird too, because I like this stuff too. Before we get to any remaining questions, we'd like to let you know that IHEA conducts an annual combustion seminar. That this is actually the first one of the first presentations, maybe a little more expanded of that seminar, and we do this each fall. This will be the 49th year for our combustion seminar. It's a 2-day course that covers a comprehensive agenda on combustion technology, and it's presented by IHEA member company experts. such as Michael. We also have a state safety and standards and code seminar, as well as a one-day induction seminar that run in conjunction with that. This year's fall seminars, as you see on the screen, will be held in conjunction with the Furnaces North America Expo, October 8th through the 10th in Indianapolis, Indiana. And information on that registration will be available in the spring. As a webinar attendee, will receive a $50 off the registration fee for any of the IHEA fall seminars, and we'll provide that code to you in an email after the webinar and once registration opens for the seminars. As before, if there's any other remaining questions, please submit them in the chat to the panel. Michael will be happy to reply to that. Michael's email is on the screen right now, so if you'd like to contact him for any follow-up on some questions or any other questions, I'm sure he'd be happy to get to them for you. You can also visit the IHEA website at www.ihea.org, as in the bottom of the slide there, to get additional information on training classes, meetings, membership, and other training courses that we have. After any questions, don't forget to complete the survey to let us know what you think about the webinar, any suggestions or any other questions you might have. And again, for some reason, I'm not seeing any of the questions.
We do have one more. Okay. We do have a final question,
okay.
Brian. Sorry to interrupt here.
Nope.
And here we go. It says, I have noticed in my scientific experimental studies that combustion efficiency does not give the best energy efficiency when specific energy is used as reference, especially in case of oil combustion. Flame properties define wave distribution, and that is the key element in absorption of heated targets. Changing flame properties changes absorption rates. Have you made any similar studies or observations?
My observation is that you are absolutely right. The emissivity, and that's part of the heat transfer talk. You'll need to come to IHEA in October to get all of that. But yes, as the shape, the color, the luminosity of the flame and the atmosphere in the furnace, as those change, then that will affect how the heat gets transferred to the product or to the process. So you are correct, especially with oil. It is so easy to change those characteristics of the flame with tiny little tweaks that you can have a lot of different results from the same air to fuel ratio, for example. But on a very high level, on a very introductory course, I think that introducing the combustion efficiency is a good way to start thinking about this topic. It is a little more nuanced than I might have presented it here, and you're absolutely correct. There are other things that go into the efficiency of the process aside from simply combustion efficiency. But for an introductory course, I wanted to start talking about get the vernacular and the concepts, start getting those. But yes, you are correct.
Thank you, Michael. We do have one last question here that it also may be more appropriate offline with this attendee, but let me throw this out there for you. Do you have any comparisons of burner compliance to and combustion safety, in particularly in the Gulf of Mexico operations?
Yes, we have some experience and some installations in the Gulf of Mexico region. And we have dealt with some of the compliance, and I would be happy to get into a little more detail on that topic. As you can see, there's my email address. You can either contact me directly or Kelly can get you in touch with me. But yes, we do have experience with that, and we'd be happy to help out with some of your specific questions. So.
Okay. Well, thank you very much. And again, Michael, we would like to thank you from IHEA and Bloom Engineering as well for presenting the webinar. Brian, thank you for moderating, and we thank you all for joining us and hope you have a great day.
All right, and we hope to see you in Indianapolis.
Thank you.
Thanks, guys.